Rationalizing the denominator. There is the case where when we're working with quotients, when we're dividing, you will find yourself in the position of a radical is in the denominator when you're through, which you can't just make it one fraction under the radical in order to get around that. That still is a radical in the denominator. Now, to get rid of this, we need to create a perfect whatever root it is we're looking for. In this case, we're looking for cube roots. Now, our properties for quotients still apply, so best case scenario, we mash these two things together into one fraction, and we simplify the fraction as best we can before we get started. If we immediately try to rationalize the denominator, it just means there's going to be simplifying to happen later. So for starters, made as one fraction, I can individually take care of things like y over y and x over x to the fifth and simplify this to be just the cube root of 6 over the cube root of x to the fourth. Cube root of x to the fourth is also something that can be simplified before we get going. Cube root of x to the fourth actually is x times the cube root of x. I'm at the simplest version of a radical that's remaining in the denominator right now. Since it's a cube root, I need to create a perfect cube. The best perfect cube for me to create here is just going to be x to the third power. It's the simplest cube I can come up with. Now, to do that, I need to multiply x times x squared, or in this case, the cube root of x squared, because properties of radicals will let me combine those things. Now, I have to do cube root of x squared over the cube root of x squared because I want to multiply by a creative value of 1, not change the value of the expression. The cube root of x squared over the cube root of x squared is 1, no matter the value of x. Now, in doing that, in the denominator, we get the cube root of x cubed, which, again, we can evaluate that. The cube root of x cubed is x, so our denominator just becomes x squared, no longer a radical in the denominator. Now, what if there's more pieces involved? Or what if it's numeric values? We're still after the same goals. In this case, we get the fourth root of 6 in the denominator. There's no simplifying that can happen. There's nothing that we can do before we try to simplify, to rationalize this denominator. Fourth root of 6. The perfect fourth that I'd be looking for is 6 to the fourth. Doesn't matter what that number is, we'll write it as 6 to the fourth. And to get there, 6 to the first times 6 cubed is what gets me 6 to the fourth, so I multiply by the fourth root of 6 to the third over the fourth root of 6 to the third. I multiply by 1. I'm just very picky about the way I make 1 look. In doing that, 6 cubed is 216. The denominator becomes the fourth root of 6 to the fourth, which in turn is just 6. Now I'm left with 2 times the fourth root of 216 over 6. I can simplify a little bit more and get the fourth root of 216 over 3. That's how we rationalize the denominator.